Hello, everyone. Welcome to another episode of Cuda Education. This is the Vulkan API discussion series, and we are in episode 3 of the gears.cpp collection. So, gears.cpp is an algorithm created by Sascha Willems. As you can see here, it is a freely available set of examples on GitHub that is meant to help the world learn the Vulkan API. Definitely check out GitHub if you want to get access to the algorithms. Basically, what we're doing is we're going through the different examples and picking apart the algorithms to learn the Vulkan API. If you want to join in on the fun, definitely check out tutorial number 1 and tutorial number 13. So tutorial number 1, I'll have the links down below. Tutorial number 1 is installing the Vulkan API on your Windows-based machine. Tutorial number 13 is installing the examples. So like this is one of the examples on your Windows-based machine. Now, it's a Windows-based machine that has a Vulkan-capable GPU. So you need to check that whatever Windows machine you have, that Vulkan is able to run on that on the GPU for the machine. It could be an external GPU, or it could be an integrated graphics card. I don't know, but you need to make sure you do that research before you get tutorial number 1 and tutorial number 13, and think you're gonna run this these examples. So. Basically we're now on the 3rd video. Check out the first 2 videos of the gears.cpp set, and yeah, we are pretty much, so the first 2 videos we did prepare vertices and set up descriptor set layout. Okay, so now we're on prepare pipeline. All right, so let us spend some time on prepare pipeline. I have to do this little spiel so that you guys have some context and sort of, understand where I'm coming from. So the pipeline it's a simple concept, but it's kind of abstract at the same time. The way I think of a pipeliner generally is it's a line of things in series that basically leads to your computer screen at the end with pixels rendered on it, right? And the series of things that happen before you reach the pixels on your screen is basically to help the computer or the API or the Vulkan API understand what it is you want to be rendered on the screen. All right, simple concept, right? But things get a little abstract for those that are not well versed in computer graphics, such as myself. All right. So what you will find is that there are a lot of different words, vocabulary used to help you as the programmer communicate to the machine or to the Vulkan API or to the computer exactly what you want to happen when you want it to happen. Another way I could rephrase it is that Vulkan is a sophisticated version of Lego. So you remember as a kid, you had Lego blocks, and you used one Lego block and put 2 Lego blocks and 3 Lego blocks and 4 Lego blocks together to build something. All right? If it was a proprietary kind of Lego box like Star Wars or something, obviously maybe you'd have special shaped Legos or special colors or special, relationships between how the Legos come together or attached together. It's the same thing with Vulkan, right? Vulkan is a sophisticated version of Lego. The thing with Vulkan is that, generally speaking, or commonly, the most primitive Lego block is a triangle, okay? So we're basically trying to tell the computer, hey, I have a triangle here, and a triangle is made up of 3 vertices, and this is how I want all these triangles to come together. This is how I want the relationship between the triangles. This is how I want each vertices to be treated in the triangle. This is what I want to happen with each vertices. So maybe, you know, not only do you have a triangle from that vertices, but there's something else happening with that vertices, right? So after going through this prepare pipeline section, I kind of had I learned a lot, and I had a greater appreciation for just Vulkan in general. And I think, you know, I'm starting to understand really in a real sense, you know, what we're trying to do and what Vulkan is trying to do and all that stuff. So yes, pipelines is a little bit abstract, but it is also, I mean, it's very concrete in terms of the high level, but then when you get into the nitty gritty of it, it can get sort of abstract. The only way I could say you could combat this is you have to increase your vocabulary of computer graphics and Vulkan. So you need to know what a primitive is. You need to know what input assembly means. You need to know what rasterization means. You need to know what depth stencil means, right? What else is there? Multi-sample, right? you need to know shader stages and shaders and viewport. You understand? Like these things you kind of need to know. I'm slowly getting to understand what it really means. And I'll probably make a video just talking about words and sort of what I think they mean. I don't necessarily feel I'll be 100% correct, but you know, it's important to kind of understand what Vulkan is, you know, what these words mean, because when you look on the spec, you know, the spec is trying to say, okay, you have this function here or this type of variable, this is what it does. And what the spec tells you, it uses a bunch of like words that you need to know the meanings of, because the spec is trying to communicate an idea or a thought, or maybe an abstract thought. And if you don't understand the words, then you kind of get lost in the shuffle. And that's the reason why people find computer graphics difficult. Because it's a lot of little nuanced words that if you're not in the industry, or if you're, you know, you haven't really been around long, it can get intimidating. But I promise you, anything that you want to learn, just hang around it and read as much as you can and do as much as you can, and eventually it will all come together. And I think that's what's happening here. Now, remember I said Vulkan is a sophisticated version of Lego. The powerful thing with Vulkan specifically is that it gives you low-level granular control over everything, which is a good thing because you have a lot of power once you learn the API. But the bad thing is that it requires a lot of instruction, right? So you know that the common knock with the Vulkan API is that, hey, to create a triangle, it's so much more lines of code than OpenGL. That's a blessing and a curse. The blessing is that you have control over exactly what you want to render on the screen. And you also not only have control over that, but you also have control over performance, because you could tinker with things to be more efficient and, you know, take advantage of modern hardware features and all that. You know, so that helps with the with performance side, and then of course you get to control what you see on the screen. You contrast that with OpenGL, where it's like, first of all, it's a collection of like legacy code and framework from prehistoric times, and then it's sort of like, you know, use this function to do this, but that function is really doing a bunch of other functions behind the scenes that you don't either know, you don't have control, or you know, you can't change or anything. So yeah, you could get a triangle with a few lines of code in OpenGL, but you don't really have much control over many things, and the performance is probably slower because, you know, it's long-winded, and it's implicitly calling other functions with your one function call, and it's just you know, not something for the future. So just take the time to learn all this stuff, learn all the lines of code in Vulkan, and you know, you'll be better off for it. Remember, augmented reality is coming down, VR, all this other stuff. So, you know, like and subscribe to the channel. You know, get some of your friends to join in on the front. Maybe have a bunch of your friends just work through the algorithms also, and learn the Vulkan API. All right, so let's get to code now. So, all right, as I said, already did prepare vertices, set up descriptor set layout, and now we're going to do prepare pipeline. All right, so the first thing is, where is it? Okay. So the first thing is VK input assembly state create info variable. It's input assembly state variable, right? And it initializes a helper function from Sascha Willems called pipeline input assembly state create info, right? So if we go to the definition, the first thing is of type VK primitive topology. Then we have like some kind of flag, and then we have like a Boolean you know, switch, right? But basically for this input assembly conversation, what is it? What it is it's basically it's telling it that it wants triangle primitives, okay? So what this is saying is that every three vertices is supposed to create a triangle. So for example, if we give if we give the Vulkan API 33 vertices, then the API should say, okay, it's 33 vertices. I want 11 triangles, right? 11 times 3 is 33. Okay, so that's what this topology conversation is about. And obviously in geography, and if you've heard the word topology before, you know you're kind of talking about a landscape. The profile of a landscape, is a landscape mountainous? Is it flat? Is it, you know, gradient? You know, does it have forests on it and all that stuff? So that's what this is about. So pipeline input assembly, okay? And if we run our algorithm here, we're going to see that it is, you know, it renders the gears, but I know it doesn't necessarily look like triangles now, but you know, I'll make the case that it is using triangles to assemble this thing, right? That's sort of what this topology conversation is about. But let's hang out with this particular option right here. So if you either Google this, or if you want to, you Google this right here, you're going to come up with a bunch of options that we could use to change exactly what the primitive is. And the primitive in Cuda Education definition, the primitive is the baseline structure of what you're trying to assemble. So like if it's Lego, it's like a simple Lego block. In this case, the primitive is the triangle, right? But it doesn't have to be a triangle. It could be a point, okay? So if we run this, you're going to see now that instead of triangles, we get points, right? And of course, you can't really see it, but rest assured, we said, hey, Vulkan, instead of it being triangles, I want points, okay? All right, you kind of get the idea. All right, but let's play around with it some more. Let's do, instead of point, let's do line. And you see now, you kind of see now in a realer way all these lines. Now, you know, I'm not going to sit here and figure out exactly how Vulkan is processing all of this. But, you know, even with the line thing, you could see like sort of, you know, these are two triangles together and all that stuff. But you see, you kind of get the gist of what the. So you're giving Vulkan a type of primitive, and you're saying, okay, build these gears with these types of primitives, right? But you know, for all you creatives out there, this is where you can go gangbusters, because you will sit here and try and figure out what exactly is the what exactly is a primitive itself, like what we're gonna do right now, and then why is it not? Is it? Let's see if it go render it. Right. You see, now this is some kind of fan situation, right? You guys, you creatives will sit here and try and figure out exactly what the primitive is and how they're relating to each other. I'm just looking at it just to see that something changed, and that yeah, something changed, and that I have this as an option, right? Let's do never tried. All right, I never tried this one. So this is triangle list with all right. Now, I don't know why just with adjacent. I don't know why this thing doesn't like it, but okay. When you look at this, oh, I ADJA. Right. All right. So this is triangle list with adjacency. Okay. I don't know. All I know is that this is an option that I have, and basically it's dealing with the relationship with all of these things. Okay. So I'll leave it to you creatives, you creatively inclined, to figure out exactly what's happening. But there's a whole bunch of things that you could do to play around with this. Let's put it back to where it was before, just so it doesn't mess up all the other things that we're doing. All right. So we could play all we want, but just make sure that you put it back to what it was, so that we have a clean slate. All right. So let's just do a sanity check, make sure that it's what we expect. All right, we're back to where we were. All right, so that's topology for you, and that's the input assembly. Again, I like to do this go to definition thing, and you kind of figure out what variables it's putting in. The flag now is, it's not being used, so I'm not going to spend time on that. And then VkFault, it's basically it's a flag to tell Vulkan how you want to restart building the vertices. You can research it on your own. Just Google this, and something in the spec will come up. But it's basically how you want to rebuild. If you were to rebuild all the with the vertices you give Vulkan, and you wanted to rebuild it, how would it go about doing it? It's I don't fully understand it right now. It's VkFault, so we're gonna move on. I'm not gonna spend time on that in this video. All right, so that's input assembly state, right? Next thing, VK pipeline rasterization state create info. That's the variable that we're creating, guys. Rasterization state, obviously it has a helper function, and we're gonna go to that helper function. Pipeline rasterization state create info. All right. What are the parameters of this function? Polygon mode, cull mode, front face, and rasterization state flag, I think, is set to a default of 0. Okay. Right, it's set to a default of 0. And we're gonna work through this. Notice too, guys, that even with the previous one, that these are the variables that are accepted, but then it creates like you know, it fleshes out the variables here. So, you know, Sascha kind of makes it easy for himself, so the algorithm itself isn't too long, number one, and number two, he's probably Vulkan initializers.hpp. He's probably using this file in all of his examples. So he wants things that are reusable. So he doesn't want to be typing out the same stuff in every particular algorithm. He just wants a helper function, a helper, a header file or whatever, that he could just reuse the same things to do similar things that he wants. Obviously changing the modes and stuff. Anyway, all right, so we're back to rasterization. So we have these things, and then it does a bunch of stuff with the variable and then returns a variable, okay? But polygon mode. All right, polygon mode. So what the hell is this? Okay, so we already have polygon mode fill, but we're gonna play around with it. We're gonna change it from fill to point. I'm not gonna sit here and try and verbally tell you what it does. What I will do is just show you, and then you make of it what you will. All right, so point basically does what the triangle primitive thing did before. All right, so that doesn't really help us. Let's do line. Let's do line. All right, let's do line and see what it does. All right, so line, I think, does basically what it was doing before. So maybe it's the same thing. I don't, you know, it's a similar thing. Fill point line. All right, let's see what this does. It's this polygon mode thing is called polygon rasterization. But again, yeah, it kind of gets murky for me. But as always, guys, you could put these keywords into Google and the spec will come up and show you exactly what it is. I'm not allowed to show the spec in my videos, just for accuracy's sake and stuff. They kind of frown upon that, so I have to respect their rules. But this polygon mode thing, polygon rasterization. So that's what that is. Do I have any other options? No, those are pretty much what I have for polygon mode. But you could do a little research yourself and sort of see what's happening here. So if you look, you will see we're back to what we were before, okay? So let's leave the polygon mode. The next one is the cull mode. And the cull mode is which triangles you are going to discard. So again, we're dealing with a computer, and the computer doesn't know anything unless you tell it. So let's say you give it a bunch of data, a bunch of vertices, and like you give them 33 vertices, and that 33 vertices makes 11 triangles, but you don't necessarily want all 11 triangles. You only want 9 of the triangles, or you only want 8 or 7 or 6 or 5, or every other triangle, or something like that, right? This is my simplified version, but the cull, if you just look up the word cull in the dictionary, it means to kind of curate, discard, delete to a specific number or to a specific amount or what have you. So this cull mode back bit it's saying back-facing triangles are discarded. Okay, so you know we ran the algorithm normally, and that's what's happening. The back-facing triangles are discarded. But we're gonna change it. Let's change it to the front-facing triangle, right? And let's see what happens when the front-facing triangles are discarded. Right? This is what happens. And you see, you start getting all kind of visual effects. Creative guys, you creative guys, I'm talking to you. This is opportunity for you. I don't really know. All I know is that they don't look right. There's some kind of visual thing happening here. Like, you see how like it's weird, dude. But that's how powerful the Vulkan API is. You could do all of this stuff. What I will say though is that it seems like, I don't know if it's a camera system doing this or what, but it seems like generally speaking, the light is a lot dimmer on this, right? So I don't know. You know, under the normal algorithm, there's the front side is very shiny and then the back side is dark, but on this everything is dark. All right, but I'm not gonna get into that. Let's change this to none and see what happens. All right, now we're at none. And I don't think much changes really. At least I don't necessarily feel that. All right, so none. I don't know. We're not deleting anything. All right, let's do another one. Let's do. All right, so if we call front and back, April Fool's Day for you guys. If we call the front and back, then obviously nothing shows, right? So all triangles are not being rendered, right? So that's pretty much it. Now we're gonna go back to the default, which I think was back bit, right? So the back facing triangles aren't being shown. Let me just see something. Yeah, I mean, obviously something is going on here, but I don't know. All right, so that's your call mode. So now you guys understand what this call thing is in the rasterization state, pipeline rasterization state situation, right? So that's what the call mode does. Now, next order of business is front face clockwise. And that is, so we're going to change that now from front face clockwise to front face counter, right? And that's what that does. Right. So this front face thing is interpret polygon front facing orientation. Yeah. You creatives, you could have at it. I'm not, yeah. But basically you could do more research and experiment with it. What I suggest happens once you get a little bit proficiency in Vulkan is that you start creating your own shapes and start tinkering with the options. And when you do that, you're gonna be able to see exactly what these options afford you, right? But you know, my emphasis isn't necessarily on creativity. It's in just learning the Vulkan API. So rasterization state create flag is 0. It's 0 here. We're gonna move on. So we've kind of dealt with the rasterization state variable. We've dealt with the input assembly variable, and you kind of see what's going on. I'm going to take out the counter thing, so we're back to where we were. Let's just make sure we are back to where we were, right? You always want to reset and make sure things are the way they were so that when we make other changes, it is, you know, we're just seeing the change and not other things. All right, so this is where I'm gonna take a little bit of artistic license, if you will. I'm gonna skip these two things. There are sort of options with them and all this stuff, but I don't fully understand their role and their purpose, and I think it's very nuanced and sort of what have you. So I'm not gonna tackle these right now. Now, once I learn more and understand, and if these things come up in other examples and I get a better thing when I tinker with them and something changes or whatever, then I might circle back and come back to this. But I'm not going to mess around with these so far. This one, depth stencil state. Let's go to the helper function. I mean, obviously this has to do with test, right? So one thing I do know, whatever this is, this has to be the same thing. So if this is true, then the other thing has to be true too. So false and false, right? All right. So let's run that. All I could say is that you can see that there's some kind of change that's happening, especially with this right here. You can see that there's some kind of change that's happening based on the depth. But, you know, I don't really know. I mean, obviously, if you look at it head on, it kind of looks like what it's supposed to be. But then there's like some processing that's happening where, and this one is way wider now, you know, but I don't know. You creatives, come on, creatives. I'm depending on you to tell me exactly what's going on. But yeah, that's what's happening. If we put it back to true and then compare up less or equal, vk compare equal, right? If we get this back to true, you see now it's a little bit truer, like sort of just goes in between each one, right? So that's your depth stencil experiment. All right, the official definition of this guy is to set depth stencil operator dynamically for a command buffer. I'm just Googling this guy right here to figure out what it is. Comparison operator for depth, stencil, and sampler operations. So there are a bunch of options with this. So let us play around with this. Let's do. All right, so never shows nothing, right? Go figure. Let's try another one. I don't think anything changed. I didn't really plan to play around with this variable, but since I'm here, I'm just curious now. Aha. So in this view, it sort of shows, but then you see how creative Vulkan is? You have all of these options of how you want things to visually be displayed. Listen, if you guys make the next avatar, you guys got to mention me, okay? Or the next thing that is bigger than avatar. I don't know, but I'm not gonna spend much more time with it. But that's let's make sure we're back to where we were. Right. So that's your depth stencil situation, right? Okay, so that's depth stencil. Viewport. I tried playing around with it, but it wasn't really much of value. Viewport state. We could look at the definition, viewport count and scissor count, but you know, I'm kind of gonna skip over that for now. Multi-sample state. The thing with this is if when I change this, the system crashed, right? So I don't really know what this is, but basically it has to be this or else the algorithm crashes. We could take a look at it though. All right, sample bit count. Well, I mean, sorry. Rasterization samples. I don't really. Dynamic state enables. So this is just defining a vector of VK dynamic state. And this is taking this variable and plopping it into here and creating another variable called dynamic state. All right. Now this is, we're loading shaders from a file. I don't really want to show it to you right now, but basically, we're loading SPARE-V files. So it's like hard-coded data that's like transferred into a SPARE-V situation. And we're saying for the first file, you know, the first file is for the vertex, it's vertices related data, and the second file is like color related data. I don't really want to get into these right now because it will kind of distract you from sort of what we're focusing on here. But basically you have some hard-coded text files, and then those text files are basically converted into SPARE-V files, and those SPARE-V files is what's being processed into the Vulkan API. I believe this is how we officially sort of communicate the data of the vertices and what we want, and then the color information and what we want. Sphere V is, I believe, a proprietary file format from the Kronos group. It was developed by the Kronos group. And the purpose of the Sphere V file format is to make sure that there is consistency across multiple GPU manufacturers. Okay, so in the olden days, what used to happen is that every manufacturer would take computer graphics data and information, and they would sort of have different drivers, right, associated with their particular graphics card. So you're talking about AMD and NVIDIA and even like Intel internal graphics cards, right? And then different models within the manufacturer's ecosystem. And what will happen is that the data that's how the algorithm that the, let's say it's Konami or Square or someone is making a video game, how the algorithm would be interpreted by each of these cards would be slightly different. It will be slightly different in very nuanced ways or what have you, right? The interpretation wouldn't be spot on from manufacturer to manufacturer to manufacturer. So because the interpretation wasn't spot on, you often had a lot of crashes in video games. You often had a lot of like system crashes. You often had a lot of like, you know, you always had to be updating drivers and like waiting for the latest release from a specific manufacturer for a specific graphics card, because, you know, unless you couldn't play the game, or if you reach a certain stage, it would all of a sudden crash because it's trying to do an operation that it wasn't consistently being interpreted the same way by each graphics card manufacturer. All of that stuff. I'm not gonna get into it too much because, you know, it's beyond the scope of this, what we're trying to deal with here. But just understand, Sphere V now is what it's supposed to do is to lock down and make sure there's consistency across all graphics cards. So no matter which graphics card you have, the Sphere V code should be the same for all of them. And that Sphere V code now, you know, with the way how it's laid out, it's supposed to be interpreted consistently across all of them. I believe Sphere V is a even lower level language. So it's like, because it's so low level, like you can't really like misinterpret it because it's so simple and basic and whatever. That's my version of it. There are other people that have way more knowledge on this, and you could look it up. SPIR-V is sort of how you spell it. Or maybe it's not -V. Yeah, I think it's -V. All right, so that's that. Vertex information is communicated and color information is communicated. What colors I want and whatever. And that's a predefined file that when you install the Vulkan, when you install the examples, tutorial number 13, you will have all these files on your system. So remember, tutorial number 1 is to install the Vulkan API on your Windows-based machine with a Vulkan-capable GPU. Tutorial number 13 is to install the examples, and with the examples, you would get these files, and it would render it. You know, this get shader path will go to it, and then the rest of it is sort of just it's more semantics again. So we have another VK graphics pipeline create info, and then we have another initializer friend here, and this one is pipeline, VK pipeline layout, VK render pass, and VK create flag. So layout and render pass. So the pipeline layout, I believe it's just a simple variable that was created on line 30. So VK pipeline layout is just a simple variable that was created on line 30, right? So right, and then render pass is a VK render pass variable. That's created on, okay, it's a Vulkan example base. So it's part of the header file here. I don't really have much information on it right now as far as my perspective, but we'll leave that alone. And then this 0, I don't think we necessarily have to go into it too much. VK create pipeline flags. We'll leave that alone. I'm not sure what it's flagging, but what have you. All right. So as we've always said with Vulkan, the natural tempo is we do a bunch of work, we fill up a bunch of variables, right? All of this is just like background work, right? We haven't really done anything yet. We're just building variables and making sure that the variables are built correctly, that the variable is of the correct type, right? So this input assembly type is this type, that type. You notice how there's always this create info. Everything is create info in Vulkan. Create info, create info, create info, because we're trying to build these variables. This one isn't, but you know. And then basically what we're doing now is that when everything is said and done, we're plopping all those variables into another variable, of course. And this variable is also a create info, but this create info variable needs all this information. Again, we're talking about create info. It needs all this information in order to process. It needs all this information in order to process this guy here. Now this function is a Vulkan function. So now we're actually like doing something in the API, right? Whenever you have a VK function like this, in any of the things that we're doing, anytime you have VK something and it's like a function and you're dropping in a bunch of stuff, you're dropping in the device, like a logical device or, you know, GPU and whatever. The pipeline catch was, I think this is a simple variable. I don't even think it's part of the header thing. Pipeline catch object. I think I'm not gonna do it now, but I think I could like put this as null pointer and the algorithm will still run. What it is, what pipeline catch is, from what I understand, it's like if you wanted to save the pipeline, like save all the information you had this pipeline, and then like use this pipeline again in some other part, or like another application or another situation or something, you could save it into this variable and reuse the pipeline somewhere else. Now, I'm not 100% on this, but what I think it's basically saying is that we're building gears here, right? And the gears is there's the gears pipeline, okay? The gears pipeline produces what? It produces these gears. Now, if you're trying to create another scene somewhere else, and in that scene, you want gears to be in the scene. What I think it's saying is that, hey, you could use this pipeline cache variable to basically cross-pollinate and say, okay, you want gears in this scene? I'm not going to redo all this work. I'm just going to reuse that pipeline cache that I had from some other situation and just put it into my scene here. That's what I think it is, but I'm not going to, you know, that's all I'm going to say, you know. VK create graphics pipeline, okay? This is in the Vulkan core situation here. So what we see here, VK create graphics pipeline, device pipeline cache, create info count, VK pipeline create info, fallback pipelines, right? So this is going to be, I believe this is going to be now our handle, right? This is going to be our handle now to refer to the result of this. And where did I see solid again? Is this the first time I'm seeing solid? Oh. Okay. All right. So this is our handle now to the result of this. So this is our handle to the pipeline, the graphics pipeline that's created. whenever I say handle, I mean literally like a handle. Like if you have a bag, the bag has a handle, right? And you use that handle to pick up the bag, move the bag, all that stuff. So whenever we want to refer to this graphics pipeline, we basically use this right here. Okay, so it's a handle for it. So it's like this function creates something, but then we need to refer to that thing that is created. And the way we refer to the thing that it created is this pipeline, that solid thing. And then just notice real quickly that this variable actually was initialized here in the gears.cpp algorithm. So it's a structure called pipelines, and then it has a substructure called solid. So pipelines.solid is a VK pipeline. Now, of course, at this point, it's just created as like a initialized variable, but it doesn't represent anything. Okay. But then when we get to here, now this is referring to what the result of this function. So whatever this function produces, it's now plopped into this variable. So now we have that. All right. The other thing that I wanted to discuss real quick is that, you know, we practice good housekeeping here at Cuda Education. You've heard me say this before in a lot of other videos. We are a squeaky clean people. If we use stuff, we put it back where it was. If we create stuff, we make sure we destroy it so it isn't lingering around everywhere. All right. VK destroy pipeline. See, we're destroying the pipeline on the device. And I don't know what this null pointer is, but we're destroying the pipeline that we created on the device when we're running the deconstructor. All right. Tell you a quick story about deconstructors and cleaning up after yourself. So once upon a time, it was intimated to me that there was a situation where, you know, they're building something in space, and there's a thing in computer science called memory leaks, right? And there was like a bid out there. I don't know if it was a government. I don't know. You know, this is secondhand information I'm getting. But basically, there was a bid out there to say, hey, anyone in the world that could build me a system. Obviously, it's a very complex system with millions of lines of code, especially when you're dealing with like space and stuff. Anyone that could build me a system that guarantees that there are no memory leaks, you'll get millions of dollars. We'll pay a premium for it. It'll be a you know, it'll be a very prized thing. But you have to guarantee to me that there are no memory leaks. What do you mean by memory leaks? It means basically that if the system is on and the system is running for a very long time, and I'm not just talking about a day or two, I'm talking about years upon years, right? Or even forever, that over time, the system doesn't have situations where it's consuming memory, but then it never destroys or reclaims back the memory. So you might have a video game or some process that's running and it's slowly consuming memory to do something, do some task. But you have to make sure that while it's running, that when the task is finished or concluded, or you don't need that piece of memory to do anything anymore, that the system reclaims the memory. Okay? What does it mean in what we're talking about here? It means that you have to make sure that you have a deconstructor and that you're destroying the pipeline, right? The graphics pipeline that you created. Because if you claim memory and you don't release it back or free it back up, eventually you're going to run out of RAM. Eventually you're going to run out of hard disk space. Eventually you're going to run out of resources. And then your system is going to crash. And then it puts the whole operation at risk and all that stuff, right? So we here at Cuda Education, we do very good housekeeping, and anything that we create, we make sure we destroy. Well, in this case, you know, this algorithm does it, right? So you run the deconstructor, you make sure you destroy what you created. Because also remember that like all of these things too that we're doing, and then of course you're taking the data and you're processing it in all these different ways and have all these instructions. This is taking up resources. So if you're eating up the resources, maybe if it's like something, an algorithm that just runs for a minute or two, you know, obviously your system memory is so cheap nowadays that, you know, even if you didn't destroy it, it wouldn't necessarily cause a problem because you have so much memory. But for mission critical stuff, the things that run for a long time, you know, yeah, you're gonna get into that problem. Anyway, guys, this is the graphics pipeline. I've done my best to kind of go through this portion of the conversation. I feel that I feel that we're heading in the right direction. I do feel that this really helped me to kind of understand Vulkan more, because you kind of see why it needs all this information. Because remember, a computer is basically dumb, and it does what you tell it to do. And if something is unclear, then it just doesn't know what to do. So you have to be very explicit in what you're telling it to do. And you know, this right here is the holy grail, right? All of this is compressed into this so that you could put it into here, and you could run this function, and then now you have your pipeline. All right. So if you guys want to comment below, you know, add some. Just all I ask is be constructive. Don't start to, you know, half of you guys that are negative and whatever, you don't even know what I'm talking about, and you have no expertise whatsoever. So if you do have expertise and you do what have you, just, you know, in the comments, discuss it. Let me know. Other people that are watching the video can benefit from it too. Yeah, and tell your friends, get a bunch of your friends together, learn some computer graphics. If you're artistically inclined, guys, if you are artistically inclined, you have to know computer graphics. It's coming one way or the other, right? And if you know this, you're way better off than people that just know like the graphics engine, right? Because the graphics engine is this high level, and it's like it can only do what the tools allow you to do and all that stuff. You know, you can't really get into the nuance of stuff as easily as if you learn the code directly. You learn the machine level kind of directly, because then you could start tinkering with stuff in ways that it hasn't they haven't done or they haven't provided a tool for you to do otherwise, right? And that will be a competitive advantage for you. I'm sure, like even with Avatar and stuff, they're building stuff from scratch. They're not just using like high level tools to make all these animations. They're like, you know, but that's why it's so expensive to make, and that's why only certain people can do it, because it's mission critical, and you need a James Cameron or something to get it done. So I think this algorithm, it knows this is front facing, right? Because the light is on this side. The sun or the light bulb that's shining on this, it knows that this is the front, and then this is the back. When we did all back or something, or back facing only, everything was shaded out. So, you know, I don't know, but that's for you creatives to figure out. All right, guys, like and subscribe, share. Tutorial number 1, install Vulkan API on your machine. Tutorial number 13, install these examples. Let's get going. Let's learn something new today. Tell your friends, like, help the channel out. Obviously, the more the better. Yeah, we're learning some Vulkan. All right, guys, bye.